All right. All right. I believe we got everything all set up. Multiplicative changes. That's a real mouthful, but obviously has the root word for multiplication. Multiplicative. Okay, so I'm not going to give you like a like rules or something like that. We're just going to do it by example. That's going to be the easiest way to do it is to just to do it by example. Essentially, you're going to use an equation, right? And this equation expresses some physical model. Could be like the velocity equation, the acceleration equation, or any of the other equations that we've looked at. The d is 1/2 at squared plus v naught t, or v squared equals v naught squared plus 2ad. These are equations that relate the different properties that are involved under different circumstances. Let's see if I can improve the focus a bit. I think that's a little better. Okay. I'm going to start with very simple equations, equations that you definitely know and it will make sense to you, and then we're going to go on to more challenging equations. And so let me write what the question is. Okay, so the question is, how does the distance change when an object travels twice as fast? Okay, so we're going to essentially almost kind of make like two calculations. I'm going to show you what the original distance would look like, and then we'll make the change and we'll see what happens to the distance. Okay, so the original equation would be this. One thing really important to understand is that I have already solved it for d, okay, because d is the subject of my question. I want to know what happens to d, and the easiest way for me to see what happens to d is to make sure that everybody else is over on the other side. Okay, so the equation is v is equal to d over t. But because the question is asking about the distance, I want to solve it for the distance, and then I'll make an adjustment to this guy. Okay, so that is my original distance. D is equal to some velocity times time. Now what I want to do is I want to make a second calculation, d prime. This will be the new distance. This will be the distance after this change has occurred. That would be equal to, and I'm going to put in parentheses anything I changed. I only changed the v. So in parentheses I say 2 times v, and then that's going to be multiplied by the same time, right? Because it would not be a fair comparison if we changed the time also. So we're only changing the speed, and we want to know what happens to the distance. Now, at this point, what I want to do is I want to return back the original equation, and I can see it. It's right there. V and t. I want to get those two guys back together. So I'm going to say that d prime is equal to 2 times vt, and that was the original distance, right? The original distance was v times t, the same v and the same t. So now what I can say is that the new distance is 2 times the old distance, right? Because the old distance was v times t, and I have v times t. So essentially the basic premise of how you're going to do this is you're going to establish the equation that's being used. It's always going to be an equation. It's some physical model that describes the relationship between two or more properties. Okay, you're going to write it in its original form, and you're going to solve it for the one that you are interested in knowing about. I want to know about distance. I want to know the effect on distance. Once you do that, you have the equation written, then you're going to rewrite the equation for a new version of d. We'll call it d prime, or you can call it whatever you want, d1 and d2, however you want to call it. But this is the new d. And then all I'm going to do is put in whatever changes. There was only one change, so that was pretty easy. And then I'm going to separate the changes from the original equation. I'm going to look through there and find the original equation. I'm going to pull it out, and whatever stays out there, that's what the change was. Okay, that's what the change was in that thing. Any questions so far while we get ready for the next one? Let's do another distance one. This time we'll go vertical. Oh, sorry, can't even see. How does the distance change when an object falls for 3 times longer? Okay, so we'll increase by 3 times, but we're going to change the time. Okay, so you drop an object, you let it fall for 1 second. Okay, how would that distance compared if you had let it fall for 3 seconds? How much farther could it have fallen if you had let it fall for 3 seconds rather than for 1 second? Okay, so in this particular case, and one thing I just want to point out to you is they will tell you the equation usually. Okay, I wouldn't say always 100% of the time, but most of the time they're going to let you know this is the equation we're talking about and what they want you to do with it. This time our equation is d is equal to 1/2 at squared. Okay, so if we drop something, then the initial velocity is 0, so we can ignore the v naught t over here, and this is the equation. It's already solved for what I want. It's already solved for distance, so great, I don't need to do anything. So then the next step is d prime. Okay, in this case, it's 1/2 a, and now I'm going to put the 3t in there and squared. Okay, I want you to really pay attention to what I'm about to do. I know your instinct will be to bring all the numbers together, like the 1/2, and then we're going to end up with 3 squared, and you probably are going to want to bring that together to make that into 9 halves. But that is the wrong move. Okay, and the reason it's the wrong move is because this 1/2 was part of the original equation. So I need it to still be there. So when I extract out the original equation, the 1/2 needs to be there. So you need to avoid this instinct that tells you that you want to combine together all the numbers, right? All these things, these factors that are in front of those variables. You want to bring them together and consolidate them, but it's the wrong move. Okay, I want only the numbers that are new, and the only number new is the 3, but it has to square it. So on the next line down, I would say this: d is equal to 9 times the quantity 1/2 at squared. So look, here's the 1/2. Here's the a. There's t squared, and then also 3 squared, which is out here in front. Okay, so everybody who was there in the new equation is still there, but I have separated what was the original equation. I have separated the original equation, right, so that I can see what was the change. The change was 9. Okay, it was 9 times. The distance will be 9 times greater if we triple the time. And I would make my final statement would look like this: d prime is equal to 9 times the original distance. Any questions about that one so far? All right, good. Okay, let's do one more, and now I'm going to introduce to you an equation that we did not look at yet. So this is a new equation. It'll be coming up not too much longer. Let's see how many topics we have to go through. It'll be 3 more topics away, and then we'll get to this equation for kinetic energy. Hold on a second. Let me just make sure I think about the phrasing of this question. That was supposed to be the word when, if you can make any sense out of that word. How will the speed change when the kinetic energy is doubled? Okay, so this is an equation that you guys have not seen before. I'm going to write it for you here. EK is equal to 1/2 mv squared. All right, so what's different about this problem is that I'm asking you about the speed, but the speed's not by itself. The speed is not by itself. That is going to make it really hard for you to see the math behind it if you leave it like that. So step 1 would be get that guy by himself. Okay, I'm going to kind of skip ahead because I don't want to spend a ton of time going over algebra. You can practice the algebra and let me know if you're having difficulty, and I will definitely help you out. But I'm essentially just going to give you the final answer, which is that v is equal to, so look, I'm going to multiply by 2, I'm going to divide by m, and I'm going to take the square root. All right, there is our original equation. I've got the V by itself. Everybody else is over on the other side. Now, what they said was we're supposed to double the kinetic energy. And again, I know your instinct is going to want to be say, oh, look, if I combine the 2 and the 2, that'll be 4, and the square root of 4 is 2, which is true. That is true. But now you've lost the change because one of those 2's is part of the equation. This is part of the equation. This is the change that I put in. This is not part of the equation. This is something I added to the equation to make the change that I wanted to see. So I do not want to combine these two together because I need the 2ek over m to still be there in the end. So I'm going to pull these two guys out. Oh, I almost pointed to the wrong thing. There is the original speed. The original speed was 2ek over m. But now what has come out in front of there is 1.2, or sorry, 1.4. Because that square root of 2 had to get pulled out because I wanted to separate the part that was the change and the part that was the original. And the square root of 2 is equal to 1.41. So instead of doubling the velocity, I only need to add 40% or 41%. If I increase the velocity by 41%, I will double the kinetic energy. And that is not obvious if you just look at the equation. You have to actually really work it out and think about how it's going to work. So this is the basic principle for multiplicative change. I don't think that conceptually this is that difficult, but it's easy to get lost in the math. Especially a lot of you, I've noticed like a little lacking in confidence with the math and doing some, and maybe there's a reason for that because you do some illegal things, frankly. But I do feel like your mathematical skills are there. It's like this is kind of a trivial thing, but it does take this like very careful kind of accounting and kind of fighting things that you've been taught to do. You've been taught to combine those terms. And now it's time to join the adult world and recognize that everything has exceptions. Everything has exceptions. And this is one of those cases where you do not want to combine the coefficients in front of these terms because you're going to lose the change in the thing, and then it was all for nothing then. It was all for nothing.